First of all, I introduce some basic notation. So BD is the unit ball in CD. B1 will be the special object, the unit disk. D. T is the unit is the boundary of the unit disk. So I consider as omega the unit ball or the unit polydisk in several variables, at least two variables. And the boundary of this omega is just the standard unit sphere or the distinguished boundary of the polydisk. So this is the torus TD. I consider the corresponding Cauchy kernel, and given this Cauchy kernel for the unit ball or the polydisk, we consider the Poisson kernel, such this is just the quotient of Cauchy kernel C of z zeta times C zeta z over C z z. So in the polydisk, this is the more or less standard Poisson kernel. And in the case of the ball, often this kernel is called M harmonic. Okay, it's not the real one, the real Poisson kernel, but M harmonic Poisson kernel. So I'm going to consider more or less the main objects mentioned in the title are Clark measures. So I need the notion of pluriharmonic measures because the measures under consideration will be of this type. So if I have a measure on the omega, I say that this measure is pluriharmonic if the corresponding Poisson integral is a pluriharmonic function. So, well, in particular, if my function is just a real valued function or even a positive function, as in the case of the Clark measures, it means that this is just the real part of a holomorphic function. Otherwise, just, well, if you know what it means, this is a pluriharmonic function. Okay, in the case of the polydisk, so the measure is on the torus, it's clear that my measure is pluriharmonic is if and only if its spectrum is in Z plus D in union with the corresponding negative part of the spectrum. So in this case, this is not just an object from holomorphic function theory, but just an object from Fourier analysis. Okay, so the main objects on the considerations are Clark measures. They are also known as AC measures. Okay, C is for Clark. So if we have a point alpha, the modulus of alpha is equal to 1. And we are given a holomorphic function defined on omega with values in the open unit disk. Then the quotient, say the real part of the quotient alpha plus phi of z over alpha minus phi of z, this is from the second relation we see that this is a pluriharmonic function, but also just a direct computation as in the case of one variable. No, there is no difference here because the function phi is defined on a domain omega in Cn, but the values are still in the disk, in the unit disk, so that just all the computations are all the same. So we have also the different expression for this real part. This is 1 over phi of z modulus squared over modulus of alpha minus phi of z squared. So clearly this is a positive function. Also it's a pluriharmonic function. So this is a Poisson integral of a positive measure. But and we say that we use this symbol sigma sub alpha or sigma sub alpha of phi to denote this measure. such that this is the Poisson integral of this measure. So by the very definition, this is a Polish harmonic measure just because it's Poisson integral, just the real part of a holomorphic function. So if we consider such measures on the circle, this is a well-known classical object, and even on Monday, Professor Trell gave a talk about matrix-valued Clark measures on the circle. So in this case, the situation is kind of opposite. We consider, say, scalar-valued measures, but they are defined on the boundary of omega, so on the sphere or on the torus. So Clark measures are related to model spaces, or more generally to de Branch-Ravniak spaces. So first of all, if we have an inner function, so in this case, I need also some additional notation. So capital sigma, this kind of non-standard notation, but well, small sigma is already for the Clark measure. So capital sigma denotes the normalized Lebesgue measure on the boundary, and the definition of an inner function is a standard one. Just the function should be bounded and unimodular on d omega. Also, I assume that my inner function maps to the open unit disk. So this allows to say that automatically my function under consideration is not a constant, and this allows to omit everywhere the assumption that the function under consideration is a non-constant in the function. So in my case, inner means non-constant from the very beginning. So in this case, if we have an inner function, the corresponding Clark measure, we consider the Poisson integral, and clearly just the 1 minus modulus of I of zeta squared, just by the very definition, is equal to 0 sigma almost everywhere. So my measure is purely singular, and it means that it's singular with respect to capital sigma, the normalized Lebesgue measure on the boundary, because, well, there are different notions of singularity in what follows. So just singular means singular with respect to sigma capital. Okay. So first of all, model spaces. In this case, I consider just inner functions. So first of all, we consider HP on the omega. This is a standard Hardy space on the ball or on the power disk. And as usual, we identify the Hardy space, the functions in the Hardy space, or the space HP of omega, and the space of the boundary values. Okay. If you have an inner function in the disk, then the classical model space is just H2 minus, I mean, the orthogonal complement theta H2. Well, the main idea of Clark was to construct certain theory, and based on a family of unitary operators from k theta to L2 of sigma alpha. So we fix alpha, and then just we consider the corresponding operator u sub alpha. If you have an inner function in omega, and we have several variables, in general there are various generalizations for k theta. So we consider the most direct analog today, just the same definition. Okay, in a sense, this is kind of large analog of the model space, or large model space in several variables. For this space, it's easy to compute the reproducing kernel. Just this is just the very expression is exactly the same as in the case of one variable, and here is the brief explanation. Just we compute directly the corresponding kernels. So we have a kernel for H2. We have also a kernel for the corresponding reproducing kernel for IH2, and then just we subtract we consider the difference of the kernels to obtain the kernel of K3 of the corresponding sub star of H2. I sub star of H2, this large analog of the model space. Okay, if you know the reproducing kernel, so essentially, if you're interested just in model spaces, just you consider just this setting. If you prefer a more general situation when we consider not only inner functions but arbitrary bounded functions from omega to the unit disk, then we have to consider so-called de Branch-Ravnyak spaces. So we have B, a non-constant holomorphic function defined on omega with values in the unit disk. And, well, just let us define just this space just by its reproducing kernel. So the kernel is the same as for the inner function, but we replace I by this non-constant function B. Well, of course, if we have an inner function, then our de Branch-Ravnyak space is just this analog of the model space. Okay, so the main theorem I'm going to present today is just a kind of illustration of the corresponding theory. Well, somehow the idea was to get as much as possible just to prove as many analogs of the one-dimensional theory in the case of, say, unit ball. And, well, this is not kind of the main theorem, but this is, in my opinion, quite tangible and visible illustration of the output of the theory. So if this theorem explains how to compare Clark measures and how to describe that one measure is absolutely continuous with respect to another, and in this case we also assume that the corresponding derivative is an L2. In the case of dimension 1, just this is kind of if and only if characterization, because this is just pure dichotomy. The second case is just if it's possible to characterize when, if not, then sigma is and mu are mutually singular. Well, even in the case of the ball, so in the case of the polydisk, we have no, so far this theorem, even in the case of the ball, it's clear that no such dichotomy, we have no such dichotomy. Okay, but at least we have one half of this dichotomy just for the absolute continuity. So, well, I prefer to consider those de Branch-Ravnyak spaces just to show the difference, certain asymmetry of the assumptions. So the first measure, sigma, is the Clark measure of an inner function, and the second Clark measure, mu, is a Clark measure for the same alpha of just a bounded non-constant holomorphic function with values in the disk. So one function should be inner, the other one just in arbitrary, and this is essential in the proof and just in the very setting. So we have this result. So sigma, the Clark measure of an inner function, is absolutely continuous with respect to mu, the Clark measure of our function b, and the derivative is an L2, even only if we have the corresponding function alpha minus b over alpha minus I times the reproducing kernel for the model space generated by the inner function I, and this function should be in the branch-Ravnyak space generated by B. Properties 2 and 3, they are more or less the same. So the second property says that we have this property for all W, and the third just for just one. It's easy to see that it's not so essential. But anyway, from the proof we see that these two properties are equivalent. So as I said before, this is kind of visible illustration, and just I would like to mention the ingredients and the corresponding parts of the general theory that are useful in the proof of this result. So this result is visible, but certain steps they are like of analogs of one-dimensional theory, that they are probably of independent interest, but they are a little bit abstract, and this is kind of output or illustration. Okay, so let's see. So the main construction is in the case of inner functions, if B is an inner function, not just an arbitrary bounded function with values in the disk, we have just canonical isometries. If B is just generates only the branch Ravnyak space, we have canonical partial isometries. So first of all, we need this kind of double Cauchy integral for with respect to clock measure, so explicit identity. And once we have this identity, it's possible to make working an analog of one-dimensional procedure when we want to, or we construct certain, in this case, partial isometries, like in the case of Clark, or in this more general setting, the corresponding construction was proposed by Saracen. Okay, so here is how what we do. We want to define partial first of all, we define just in the case of a disk, it's possible to, and if B is an inner function, then it's possible to construct not just a unitary operator from the model space onto L2 of sigma alpha. So in this case of B, just a bounded function, we construct first a unitary operator from the branch Ravnyak space generated by B, and it will be onto H2 of sigma alpha. So in general, this is not the whole space L2 of sigma alpha, but it is defined just as the closed linear span of Cauchy kernels in L2 of sigma alpha. So this formula gives an explicit definition, and it's possible to prove that once we define this operator on the reproducing kernels, then we have a unique extension to unitary operator from the corresponding branch Ravnyak space onto H2. So what's next? The main idea is to use the initial proposition. So once we have this, we just explicitly compute that the first scalar product in L2 of sigma alpha is equal to the corresponding scalar product of the reproducing kernels in the branch Ravnyak space under consideration. So we have an isometric embedding, and just we use the density of the family of reproducing kernels in H in calligraphic H of B, the branch Ravnyak space generated by B. we deduce that this extension is unique, and just the definition of H2 of sigma alpha says that that we map onto this space. So probably I should mention that there are simplifications if we consider an inner function in the unit ball, not just omega, or the unit ball, or the unit polydisk. In this case, just we define a unitary operator, because what happens in this case, H2 of sigma alpha is just L2, and it will be a unitary operator onto L2. And well, it simplifies the other arguments. Okay, if not, then we define also kind of opposite operator, V, capital V of B alpha, using the Cauchy integral, and then we obtain kind of not the like in this simplified situation, we obtain only partial isometry from L2 of sigma alpha into H, calligraphic H of B, the branch-Rovniak space generated by B. And if you restrict this operator onto H2 of sigma alpha, then we obtain the conjugated operator of U, the previous one. This is what we use to prove that result. So this is not the main object of the present talk, but this is kind of the general theory of independent interest here. Well, I'll skip the proofs. Probably, so this is one part, what we need in the proof of this illustrative result. And also, I would like to mention the second part from several complex variables. This is kind of F and M Ries theorem in several variables. So first of all, I consider the set M naught of the sphere. This is the set of representing measures representing the origin for the functions in the ball algebra, the functions which are holomorphic inside the ball and continuous up to the boundary. So once we have this, we say that in the previous slide, we say that the measure is totally singular if it is singular with respect to every representing measure. In the case of the unit circle, it means just a singular measure because we have just one representing measure, the probability Lebesgue measure on the circle. In this case, we have a pretty large family, and if our measure on consideration is singular with respect to all measures in this family of representing measures, we say that its measure is totally singular. And here, kind of replacement of this F and M Ries theorem is the following result. If you have a pluriharmonic measure, in particular, we look at the corollary. If you have a Clark measure, then its singular part is totally singular. So this is the kind of second ingredient in the proof of that theorem, that illustrative theorem. Okay, and probably I'll skip all this. I'll show that just a certain part. So when we prove this theorem, again, the main result today on consideration. So we use those two families of operators U and B sub alpha, B sub B alpha, and well, we use the corresponding properties that they are, well, in the case if B is an inner function just to be used, we have a unitary operator and its inverse, If not, then just up to, we have these two operators, and we use them. So how we use, I would like to show how we use this F&M Ritz theorem, or just an analog of this result on the unit sphere. And also it explains that we do need, at least for our argument, we have to consider the unit ball, not say, even in the case of the hollow disk, it doesn't work. So after certain computations related to these operators, so what we have, we obtain the following. So we see that the Cauchy integral of certain expression, of certain measure, is 0. So this is a, this implies that this is a Henkin measure. So the definition of a Henkin measure is here. Okay. This is a classical object in function theory in the ball. So it means that if you take bounded sequence in the ball algebra such that at every point inside the disk, in the open disk, this sequence goes to 0, then the limit we take the integral over the sphere, f sub j d mu is equal to 0. So the simplest example of a Henkin measure is if our measure is orthogonal to the ball algebra. If the integral is always 0, then of course the limit is 0. Okay, so in our case, we have certain measure. So its Cauchy integral is equal to 0. So, well, of course, this is a Henkin measure. And yet another analog of F&M Ritz theorem, so-called Kohl-Range theorem, guarantees that on the one hand, we have that this measure is absolutely continuous with respect to certain representing measure. But on the other hand, we know from that result on singular parts of pluriharmonic measures. This measure is singular with respect to any representing measure. So this measure should be 0. So this is kind of illustration how to prove this. Okay. So, well, I should stop here, I think.
Thank you very much.
Есть вопрос трансляции. Известна ли операторная интерпретация типа как уклад? Если можно, на английском повторите.
Вопрос повторить?
Ну, просто чтобы...
Okay. So, the operator part of the Clark theory is its analog is not exactly in this area of Clark measures, say in the ball. In the ball, we have to consider the setting that is close to operator theory in several operator variables. And in this case, there are analogs of, so we have to replace the usual Cauchy kernel by, say, just 1 over 1 minus z zeta without any power. This is a reproducing kernel. This is not the standard hard disk space H2, but it's a different hard disk space. So, well, there are analogs of Henkin measures of certain objects with the same names, but this is kind of different theory. So this one is like function theoretic part of the Clark theory. And the operator theoretic part of the Clark theory is just that operator theory in several operator variables. So this is not exactly the operator theory analog of the Clark theory. Okay, probably.